Hello everyone, my name is Dr. S. Pavan Kumar Reddy, Assistant Professor in the Department of Artificial Intelligence and Data Science, BVRIT, Narsapur campus. My subject name is Data Structures using Python. Today we will discuss about one of the important topic is data structures and in the data structures binary tree and that what are the different operations in that binary tree. See the binary tree operation. Here we discuss the different types of the operations is performed on the binary search tree. Binary search tree. What are the different operations means? We have to search the node or key in the binary search. We are inserting the node or key in the binary search tree. We are deleting the node or key in the binary search tree. Deleting the entire binary search tree. How to find the mirror of the binary search tree, how to finding the smallest element in the binary search tree, and finding the largest element in the binary tree, and determining the height of the binary tree. These are the different operations under the binary search tree. That is the simply called as a BST. See one by one operation. So first operation is searching a node or key in the binary search tree. This is the first operation in that binary search tree. The binary search tree is BST. Simply. Okay. This operation is performed to find whether the given key is exist in that tree. Whether the given key is present in the tree or not. The search operation can be start with the root node. First, you can check whether the tree is empty or not. If the tree is empty, the node or key value searching is not possible. If the tree is empty, we are not possible. Any searching operation will not perform. If the key is available, the key values is the tree is full, can search the key values. If the tree is not empty, the nodes are present in it, and search function will be checked whether the node or key value to be searched in the search, and the value is compared with the key value with the current node. That this point will be understood in next upcoming slide in that example. If the node or key will be searching is less than the value, if the node or key to be searched is less than the key value of the current node, then it can be left child node. Other than if the node or key to be searched with greater than the key value of the current node, that is called as a right child. See these points in the upcoming example, it clearly understood. This is the algorithm for searching the node. First, we are creating the search operation. Will be creating the root having the some values. First step is start. If root equal to null. Root equal to null means the tree is empty. Else, if root dot information equal to value, it can having the root node. The root node having the some value. This one. Okay. Else, if the root dot information is greater than value, root dot information is greater than value, it can be search the left child value. That is called as a root dot left child value. If root dot information is less than value, can search the root dot right child value. Else can print the value is not found. End if. Finally, the step 3 is this one. Okay, this is the algorithm for the searching the element. See this example based on this previous algorithm. In this example, we have a given binary search tree. The search node is 20. The value is 20. First, the value 20 will be searched. The value is present in the tree or not initially. First, the root node is checked. First, the root node is checked. What is the root node? 41 is the root node. If the root node is 41, this value is compared with the 20 node. Actually, this is the tree node. The example of binary search tree in the tree example. Based on this example, you can search the 20 element. First, the root node is 41. The root node will be checked with the comparing the current key value. Okay. Next step, the value will be stored at the root node is not equal to the value to be searched. Whatever the value will be searched, the value is not equal to the root node. That means 20 is less than 41. You can traverse the left subtree. What the value will be searched? The key value is 20. The 20 value is searched with the 41. So, the key 20 value is less than 41. So, the root node having the always less value with the left side, highest value is the right side. The 20 is the least value, less than the root node now. So, the value is present in the left subtree. Okay. After that, the 10 node is not value to be searched. We are not search the 10 value. The value is 20. Here, the 10 value is 20 is greater than 10. We can now traverse the right subtree with respect to the 10. Right subtree with respect to the 10. So, the 10 value is search the less and highest value. So, we can search the right side element. The next step, the 25 is not the value of the search. We are not searching the 25. We are searching only 20 value. So, the 20 is less than 25. We can now traverse the left subtree with respect to the 25. The 20 value is left subtree. Okay. Now, the value is searched. So, the 20 value is equal to searching value. Okay. That is the clear example. Now, based on that example, we are implementing the Python programming. First, we are creating the node based on the class. Here having the some values, the left and right side values. We are searching the one element now. That's why we are defining the one function. That function is called as a def search binary search traversing. In the binary search traversing having the root node and key value. Based on this key value, you can search the element in the tree. Suppose if root is none or the root dot key equal to key, that means it can be written the root node. The key value is smaller than the root key, you can search the left subtree. The key value is smaller than the root key, you can search the root dot left node. If the key value is greater than the searching element, you can search the right element. Root dot right element. This is the sample inserting the elements. We are creating the binary search. The root node is 8, left node is 3, right node is 10. The again left to left node is left node is 1, left to right is 6. Now right node is 14. This is the tree we are creating based on this example. Okay. Now the key value is 6. The sixth value is searching whether the key 6 value is present in the tree or not. Now final result will get result equal to search binary search root key to be searched. Key to be searched means which key will be searched? Sixth value is searching. The sixth value is present here. So, the key will be present in the binary search tree. Otherwise, the key is not present in the binary search tree. Understood? This is the searching element in the binary tree. The second operation is how to inserting the node or key in a binary search tree. How to insert. Now, the insertion operation is also start with root node. The insertion operation is also start with root node. First, we can check whether the tree is empty. Tree is empty. And we are allocating some memory for the new node. If the tree is not empty, you can compare the key value to be inserted with the value will be stored in that current node. If the node or key to be inserted in the less than the value of the current node, we are inserting the left subtree. Otherwise, the greater than the key value of the current node, we are inserting the new node to be inserting to the right subtree. These are the second operation, that is inserting the elements. See algorithm. This is the algorithm for inserting the node to the binary search. See what are the different steps for inserting the key. First, we can see inserting elements now. So insert root comma value. First step start with. Second step, if root equal to null, this condition is always important for the all binary search operations. Root equal to null, we are allocating this some root node, that is set root dot information equal to value. Set root dot left child node equal to root dot right child node equal to null. That is condition is yet. Otherwise, if root dot information is greater than value, we can insert root left child node less than the otherwise root dot right child element condition will be ending. This is the algorithm. This is the algorithm for the inserting the element. Based on this algorithm, we are see this one a beautiful example. For suppose we have a given binary search tree. Now we can insert the value 7. The value 7 will be inserting to this tree. Where we are inserting the 7, see one by one step. First we can search the root node. Second one, the root node 7 value will be searched now. So inserting now. So 7 is less than 41. So we will go for this side. The second one, third one, we know that 7 is less than 10. Less than 10, go for this one. After that, the 7 is greater than 3. 7 value inserting now. So the 7 value is greater than 3. So the 7 value is inserting here only. Finally, the node 7 value is inserted at right child in the binary search tree. This is the right child. This is the left child. Okay. See this code for based on that example, we are implementing the Python programming. First, we are creating the node. After, we can perform the inserting the elements. This is the condition. This is for creating the tree. We are inserting the new element. See this one, node is created by using the some class. This is the inserting the binary search tree by using the function. If the root node is none, can be written the key value. If the root is less than root dot key, can inserting the root dot left. We are inserting the right, insert dot right node after ending. So see this example, root node is 8. After the root node, insert binary search tree 3. We are inserting the 3 node. After inserting the node 10, after inserting the 1 node, after inserting the 6, after inserting the 7. Based on this data, we are creating the tree. After creating the tree, we are inserting the another new node, which is the new node. The 4th node is inserting to this tree, where we are inserting the 4th node. So the root equal to binary switched off, binary root comma new key. The 4th node will be inserting here only. Okay. The root node is less than the root node, greater than the root node. So the 4th value is less than the root node. So we are inserting the here. This is the inserting the node to the binary search tree. Another operation is deleting the node. How to delete the node or key value in the binary search tree. For deleting the node or key from the binary search, it is a crucial process, a difficult process. So the deletion of the operation can be categorized into three parts, three cases. First case, delete the node having the no children's node, deleting the node having the one child node, deleting the node having the two children's node. See one by one case. First case is deleting the node having the no children. See example. For example, this is the example of the tree. In this tree, we are deleting the no children node. We are deleting the either 6 or either 37 or either 61. Suppose I am deleting the 61 because the case is there is no children's node. There is no children. So, the 61 node will be deleting. See how to delete. Here, the 61 value is deleting from the binary search. Okay. Here, this is the 61 will be searched to the node. As the 61 is greater than 24, can traverse the right subtree. The 61 is greater than 42, we are search the left subtree. Okay. Right subtree. After that, the node have value 61 is deleted from the binary search. After deleting this node, finally the tree is like this. Okay, that is the deleting the node or key from the binary search. Another case is one child node. One child. What in the tree, which is the one child, that node will be deleted. For suppose, in this example, single node is child node having the 6 is the single node, this node is 10. Okay. Now, whatever the single node element is there, that element will be deleted. See this one. We have been the binary search tree, we can delete the value is 10 from the binary search tree. Initially, the search key is starting from the root node. We can start with the root node. After that, which element will be deleting? 10 value is deleting. The 10 is less than 24, we can traverse the left subtree. Now the node is deleted is found and also node. The node is founded with this stage. This node will be deleting. After deleting this node, finally the tree is like this. This is the deleting the node from the binary search tree. That is the second case. The third case is which elements are the two child nodes. The two child nodes element is deleted. See this one. We have the given binary search tree. This one is the binary search tree. Now we can delete the whatever the two children's node elements are there. The two children's element node is 42. This 42 is deleted from the binary search tree. 42 value is deleted. First we can search the root node. The 42 is less than 24. 42 value is deleted. This 42 is less than 24. So we can traverse the right subtree. Right subtree. And finally we can delete the 42. The 37 is go for the root node. So finally we got the after deleting the two children's node. See this is the algorithm for the deleting the node. First case is single child, no child and two child. These are the three cases. The three cases are available in that one. Starting the node, if the root equal to null, as usual, if the root node dot information greater than value, we can delete the root dot left child. Root node information dot left than the value, can delete the right child. If the root dot L child node equal to null and right child equal to null, okay, we are creating the root. If the root dot L dot child and L root dot right child, can find the target. This is the target for the binary search tree. Okay. Now the next operation is we are deleting the entire binary search tree. Up to now we are deleting the some nodes, either inserting the node or deleting the nodes. Now we are deleting the entire binary search tree. How to delete the entire binary search tree means it is very easy to delete the entire binary search tree. First, we are deleting all the nodes in the present in the left subtree, that can be followed by the node is present in the right subtree. Finally, the root node is deleted and the entire tree is deleted. This is the algorithm for the deleting the tree. Starting, if the root is not equal to null, we are deleting the left child node and right child node, and we are deleting the root node. Finally, we can delete the entire tree. That is the deleting the entire binary tree. This is the example. For this, this is the tree. Based on this tree, we are creating the node. This is as well the condition. We are deleting the node now, deleting the entire tree. So we are creating the functions by using this function. The function is def delete binary search root node. If the root node is none, can be written the none. Otherwise, we are deleting the left and right subtrees. How to delete the left and right subtrees? The root dot left equal to delete binary search for the left tree. Root dot right equal to delete binary search root dot right. After that, to delete the content node by removing the references by using this one. So this is the example for creating the node. The root node is 8. Now we are inserting the some elements. Root dot left equal to 3. Root dot left equal to 3. Root dot right equal to 10. Now we are inserting the another node. Root dot left dot left. Root dot left dot left. The node is 1. What is the target? We are deleting the entire tree. How to delete entire tree means root equal to delete binary search tree. Now, if root is none, the binary search tree having the deleted. Otherwise, binary search deletion is failed. Okay. We are deleting with the key value is 1. This node will be deleting. Next, the node is 3. This node will be deleting. Next, node is 10. This node will be deleting. Next, node is 8. This node will be deleted. Finally, we can remove the delete the entire tree. The next operation is finding the mirror image. Here, one of the finding the mirror image of binary search tree. The mirror message of the mirror image of the binary search tree means interchanging the left subtree with the right subtree. Either left subtree to right subtree. Interchanging left subtree to right subtree. Okay, that is the mirror image of the binary tree. In that is example 10, 5, 15, 2, 7, 26. This is the actual tree. Here the 5 value is left node, 15 value is right node. 15 value is right node. Now we are interchanging the from left to right. After that, interchanging this value, the 15 value came here left side. The fifth value is left side to right side. Okay. This is the algorithm for mirror image. First step is starting. Second step is if root is not equal to null, if mirror image of left side will be right child tree. Set, we are creating the another temporary node. The temporary node is set temp equal to root dot left. Root dot left equal to root dot right. This is the left node and right node both are equal. Can set the right node is temporary node. This is the end if this is the entire algorithm will be end. That is the finding the mirror image of binary search tree. The next, this is the program for finding the mirror images. First we are creating the node. This create node is by using the class node. Here the class node having the two values, that is the self comma key value. The self node initially the left node is none, right node is none. The left node is none, right node is none. After that we are defining the mirror image for the binary search tree. we are defining the one function. That function is mirror binary search tree. If the root node is none, it can be written the none. After that, we can find out the left and right subtree. Left mirror equal to mirror binary search is root dot left. Mirror right mirror is root dot right. Okay, we are swapping. Before going to swapping, we are creating the another one temporary root node. Another temporary node. Okay, after swapping left and right children, left root dot left equal to right mirror, root dot right equal to left mirror. We are swapping with the left to right, right to left. After that, we can perform the another traversing, that is another function, in order traverse function. We can defining the another function, that is def in order traversing function. If the root is none, can be written. In order traverse means root dot left, can print the root dot key is n value. In order traverse root dot right. This is the basic what are the function. Now we are creating the tree. Root node is 10, root dot left is 5, root dot right is 15, root dot left, root dot left to root dot left dot right, root dot left dot right is 7. Next, root dot right, root dot right is 6. Okay, after that, okay, this is the example for creating the tree. Based on this tree, we can traversing operation will be left to right, right to left. The nodes are interchanged. That is the basic operation for the mirror image. Mirror image is the basic operation. Okay, this is root. In order traversing the root node, can print mirror binary search tree for traversing the operation. Initially, the one side in order is 2, 5, 7, 2, 5, 7. Next 10, 15, 6. 10, 15, 6. After that, we are in mirror image is 6, 15, 10, 7, 5, 2. This is the after mirror binary search tree, like that. The next operation is smallest node in the binary search tree. Smallest node in the binary search tree. As we know that the basic property of the binary search tree is the smallest value is always occurs in the extreme left of the left subtree. Root node smallest value is always left of the left subtree. Highest value of the root node is right of the right subtree. This topic is covered in the next slide, upcoming slide. Now this topic is covered in this slide. Okay. If there is no left subtree, then the value of the root node is the smallest. Okay. Here, to find the smallest value in the binary search tree, you can simply find the value of the node is present in the extreme left of the left subtree. This is the algorithm for the finding the smallest node in the binary search tree. Algorithm for smallest binary search tree. Binary search tree. How to define the that algorithm? That algorithm has followed the different steps. First step is start. If root equal to null or root dot L child equal to null, return null. Else return can be written smallest value of the root node. Okay, this is the algorithm. This is the example for the finding the smallest node in the tree. This is the tree node. How to creating the tree node like this? The node is creating some class. We are finding the minimum value, minimum node in that by using the some function. That function is find minimum node. After creating the tree, we are find out the minimum node. Okay. Which element will be minimum value in the tree? 1 is the minimum value. So the 1 is smallest binary search tree is 1. Next one is the Finding the largest node in that binary search. Largest node is always right side in the root node. Right side in the root node. That is, as you know that the basic property of the binary search tree, the largest value is always occurs in the right of the right subtree. This is the root node, this is the left node, this is the right node. Right of the right subtree. Right subtree. If there is no right subtree, the value of the node will be large value. Okay. To find the largest value in the binary search tree, can simply find the value of the present in the right of the right subtree. This is the algorithm for the right subtree. Largest value na, largest value always in the right side of the root node. That is right subtree. Small right side largest binary search tree. This is the algorithm. Largest value of the root node. This one, root equal to null or root dot right child equal to value can be written null. This is the find out the largest value in the binary search tree. This is the example of the finding the largest value in the binary search tree. As usual, this is the same example. Based on this one, we are creating the node. We are find out the maximum node. The maximum node is find out the current right side. Current dot right element, rightmost element. After that, we are creating the one tree. We are finding the right side. Finding the right side element. This is the tree. In this entire tree, which element is the largest element? The 14 is the largest element. So, the 14 value will be displayed. Next one is to determine the height of the tree, height of the search tree. Here, the height of the binary search tree is easily determined. It can be determined. To determine the height of the binary tree is easy. First, you can calculate the height of the left subtree or height of the right subtree. If the height is greater than 1, it can be added to the height. If the height of the left subtree is greater, 1 is added to the height of the left subtree. Similarly, the height of the right subtree is greater than 1, we can add of the right subtree. This is the algorithm for the creating the height of the binary search. First step. Second step is you can check whether the root node is null or not. If the root node equal to null, cannot find the height of the binary tree. Otherwise, left node will be calculating. To calculate height of the left child node. After that, we are calculating the right child, root dot right child. If the left height is less than right height, that is right height is incrementing by 1, otherwise left value is incrementing by 1. That is the algorithm for height of the binary tree. See this example. This is the tree. The tree is not creating like this every time. This is the same step. This is the function for finding the height of the binary tree. The root node is none, can be written 1. We have to find out the left to height. After that, find out the right height. We are creating the tree. Finally, we can draw the what is the height of the binary tree is 2, 0, 1, 2. Okay, the height of the tree is we have to find out the leaf node to root node. Leaf node to root node means bottom to top. That is the height of the binary tree. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.